Be nice. So I've started recording. Thanks to those of you who have recorded when I haven't recorded, because that's been absolutely wonderful and really, really, really helpful. Just missed that. Minimize that. Nope, wrong button. There we go. Nope. Yeah, I clearly don't know a lot about MS Teams. So today we're talking, it's Friday, thank God. Atomic and molecular orbitals, VSPER theories, and then questions about resonance and arrows, because I'm sure you got questions about resonance and arrows. I was in a thesis defense on Wednesday. You got the joy of interacting with my, I wonder how long he got through the lecture before he told you that his PhD was from Cambridge. My Cambridge trained postdoc, Dr. John Hayward. And I know he covered a little bit about resonance and arrows, but I was keeping an eye on the chat and there was a lot of question marks. So I think we'll be talking a bit about that today. So first thing I'm going to do, and that's what I'm always going to do, is if anyone has any questions from the material that they specifically want to go over. I got one in email, which I responded to, but I think it was an interesting question, so I will bring it up here. But if anyone else has anything, kind of the, otherwise I've got 3 worked examples to work through. I am seeing nothing in the chat. If you suddenly become inspired sometime through the course or the lecture, please share. Your inspiration is inspirational to all of us. So one of the questions I had from a student was, they said, somewhere, I have no idea where they saw this. It's right, so I don't mean it as a criticism. It's not like I don't know where they saw this. That's insane. It's right. It was pointed out that this oxygen was tetrahedral. And they asked a couple of questions, which good questions, but and deserve to be answered. But I think hopefully some of you will think that's a stupid question. Others of you will think I didn't know that either. And this is the real risk, because I don't know what's a stupid question or not from you guys. So they said, why is that tetrahedral? It's only making one bond. And I think it depends how we're talking about shape. So if we're talking about the shape of things around the atom, like things you can see, like other atoms, there's only one thing. There's only one bond. So it's not clearly tetrahedral by shape. But normally when we're talking about tetrahedral, what we're talking about is the arrangement of the orbitals, an arrangement of groups around there. And so lower down on the page, they said, well, they understood why that was tetrahedral, but they didn't understand what the first one was, because are those lone pairs there? So first comment is the lone pairs are implied on the top structure. And how do we know they're implied? How do we know that there's 3 lone pairs there? Well, I've just said it's a negatively charged oxygen. And I know there's one bond. And I know it's oxygen. So if I look at my formal charge, oxygen is 6 minus the number of lone pairs, which we don't know because there's no lone pairs drawn, minus 1/2 number of E- in bonds. So the formal charge is -1 because it says so. 6 minus number of LP minus 1/2 of 2. Even I, as an organic chemist, can do 1/2 of 2. So that's 6 minus 1 minus number of LP. It's 5 minus 1 minus number of LP. Of electrons in LP, right? -1 minus -5 minus 6 minus P. Multiply both sides by -1. So there's 6 electrons in lone pairs. And the only way we get 6 electrons in lone pairs is by having 3 lone pairs. So you can always work it out that way. Oxygen almost always has 2 lone pairs. If it's negatively charged, it's got 3 lone pairs. Because that's the only way it can be negatively charged. So when we start looking at that now, this sort of leads us into today's lecture. It's got 4 things, and the way that when atoms have 4 things, and by things I mean other atoms or lone pairs or single electrons in an orbital, the only way it can arrange those 4 things is by using 4 different orbitals. And the lowest, well, let's think about this. Let's say you're oxygen. Come on, oxygen. Okay. And I'm trying to advance my slides, but I'm just not pressing the right button. So let's say you're oxygen and you're bound to a carbon and you've got 3 lone pairs. And let's say we want to draw the electron configuration diagram for this poor low oxygen. Okay, so if you're just oxygen, there's a 1s orbital with 2 electrons in it. There's a 2s orbital with 2 electrons in it. There are 3 2p orbitals. And we should have 1, 2, 3, 4 electrons in the 2p. That is the electron configuration of oxygen. Hopefully this is review for everybody. Okay. So I'm going to come back to this poor little oxygen because I want to use a stronger example that really demonstrates this. Let's look at methane. Yeah, I am. Can you see my screen, Alan? Am I sharing my screen? Can anyone else see my screen? Okay. Oh, good. Thank God. Good. Okay. I think we've reached consensus that we are sharing a screen. Okay. If you can't see my screen, leave the meeting, come back to the meeting. Also play around with the settings because maybe the screen is minimized. You can't see the screen, but the screen is being shared. So you got methane. And let's take a look at carbon's electron configuration. We'll just sketch it down here. Actually, take a second and draw it yourself. One S, 2s, 2p, okay. Hopefully that's what you drew. Right? If you remember all the rules about sticking electrons in orbitals, you start at the bottom and you move up. Carbon's got 6 electrons total. Sticks 2 in a 1s, 2 in a 2s. You pair them up. They have to be opposite spin. Somebody asked me about, does spin matter? Yes, and how you draw your electrons, but we're not going to worry about it in any other way. And then you've got 2 electrons left, and you put them into separate orbitals. You don't put them into the same orbital. Like it would be incorrect for me to draw it like that. That would be bad. Can anyone tell me why that's worse than what I drew initially? That is a tautology, Madison. Yeah, I agree. It's not stable. It's not worse. Poly exclusion. Thank you, Amber. What is a poly? You know, can you tell me anything more about why that's a thing and not just like it's not important because Poly just said it. You want to fill as many orbitals as possible. Okay, so Joshua's walking on this close. Higher energy to bond the two, then separate them. Okay, I like what Deeprashika said. So I'm not going to say I'm going to get rid of the bond thing, but it's higher energy to put them into the same orbital than separate them, because electrons are negative charges. And if they're in the same orbital, they're trying to occupy the same space, and negative charges repel each other. So we prefer to have the negative charges in separate orbitals at all possible. It costs energy to put two electrons into the same orbital. So it's cheaper for us to do that. And of course, my y-axis here is energy. So another question we got here is, why does carbon have 6 electrons and only 4 electrons? Carbon has 4 valence electrons, but it's got 6 total electrons. So this comes down to the idea of valence. Outer electrons able to do chemistry. So these are electrons on the outer side of the atom. They're the highest energy electrons. These 2 electrons in the 1s orbital are boring. They do nothing. They are sitting there in the 1s orbital. The 1s orbital is not going to do anything. It's going to stay a 1s orbital no matter what you do to carbon. I think I can say with certainty that I am aware of no cases where the electrons in the 1s orbital of carbon do anything. They just sit there in the 1s orbital of carbon. All the chemistry is taking place at the level 2. So when we talk about carbon having 4 valence electrons. That's when we're drawing oxygen's lone pairs and things. Oxygen has 8 electrons, but we're only worrying about 6 because 2 of them are buried in 1s. And we don't care about them because they're not going to do anything no matter how hard you try. What we're only interested in is the 6 electrons on oxygen, or the 4 electrons on carbon that are in the second energy shell, the valence energy shell, or the frontier energy shell, whatever you want to call it. Frontier sounds sexier. So let's think about carbon. So we've got 4 bonds to hydrogen. This is a tetrahedron. If you're properly nerdy, and as a science student you should be, it's the shape of a 4-sided die, right? And it's the reason 4-sided dies are tetrahedra is because it's the only geometric shape where you have 4 sides that are all equal in size. And that's because it's a perfectly symmetrical shape, right? All of those carbon-hydrogen bonds are exactly the same length. All of the angles between adjacent hydrogens are exactly the same. They are all 109.5 degrees. Every single every angle between every hydrogen and every other hydrogen is 109.5 degrees. It is the perfect tetrahedron. Okay, so the energies in each of those carbon-hydrogen bonds, are they the same or different? We got a same. We got a same with a question mark. We have some more confident sames. Good. I like this. Everybody's saying the same. They are all identical, and Dondra has stolen all of the thunder, and good for her, him. I'm really sorry. Them. Because from what we see here with these things, there are 4 orbitals that are involved. There are 4 bonds. Great. 4 and 4. One thing we could do is, hey, I'm going to put a little energy into the system and bump that puppy up. So now I got 1 electron each orbital. I've had to add some energy, but that's okay. We can add energy. Energy is like around, man. Especially if you listen to the New Agers, energy's everywhere. It is everywhere, of course, but not the way they mean it. So there's extra energy in there. We got 4 orbitals. The problem is those orbitals aren't the same, right? You wouldn't expect the s orbital to form a bond with the same energy as the p orbitals because the p orbitals are higher in energy. So if the other thing is the p orbitals are all 90 degrees to one another, right? If you're reading the lectures. And these things are 109.5 degrees from one another. And the S is a circle. And how does a circle make a bond with any direction? Because it's a freaking circle. So what we do is we take those 4 orbitals and we toss them in the orbital blender. Orbital blender. And out comes 4 times sp3. All the same energy. We can call these degenerate energy. Capital E stands for energy, always. Little e with a negative charge is electron. Anyways, these 4 orbitals are degenerate energy. They all have exactly the same energy. We follow the Pauli exclusion principle. We stick 1 electron in each. They're all the same energy. There's 4 of them, all the same energy. They need to adopt a geometry such that they're all equidistant from one another. Because if any 2 of them were closer to each other than any other orbitals, they'd be higher in energy because the electrons would be closer. So all the electrons are trying to get equally away from one another. And the way they do that is they become a tetrahedron. So this is the way to do it. So are carbon's valence half p orbitals and half s orbitals, or are they always changing depending on the form? So carbon, elemental carbon not bound to anything is this. So you take a carbon atom, you stick it in a vacuum in space, and you look at its electron configuration, it's that. There aren't a lot of vacuums around here, and there's not a lot of single carbon atoms. So almost always carbon's making bonds. Yes, we're going to get to this very soon, Jolene. Yeah. So the carbon's valence shell is made up of 3 p orbitals and 1 s orbital that are mixing together to generate the lowest, most stable geometry possible. So if we go back to this oxygen guy and we make a bond, well, all bonds are hybrid bonds because if oxygen tries to make a bond, just a single bond, it would try and use the s orbital because the s orbital is its lowest energy orbital. The problem is it's occupied. So we need to mix the orbitals. So we do that. Now this is negatively charged. So because it's negatively charged, we're going to add an extra electron in because somebody gave me an electron, which was very kind of them. It was probably a hydrogen atom. So if we're doing that, and we mix these together, oxygen then has a choice. And let's go through the choices. It can become sp3. If oxygen becomes, so let's just keep an eye on S and P. We can become sp3, where we have 1 s orbital and 3 p orbitals times 4. We can become sp2. If we become sp2, we're a little bit lower in energy than sp3. Because in sp3 is you add the energy of the s, you add the energies of the 3 p's, and you divide by 4. So you average them. So it's weighted mostly towards the p because there's 3 p's and 1 s going into that energy thing. So it's going to be very p-like. sp2 is going to be a little less p-like because there's only 2 p's and 1 s. So it's kind of like a 2-to-1 ratio instead of a 3-to-1 ratio. And we keep a p. And if we do that, so if it's sp, so if it's this, you know what, I should actually draw these all fucking out. I'm sorry. 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 1. if we're sp2, 1, 2, 1, 2, 1, and 1, 2, because we need to use an sp orbital to make the bond. If we're sp, then we're going to be, 2 sp orbitals and 2 p orbitals. You never, so Nora, you will never move an electron from a 1s orbital. Consider those 2 electrons locked. They will never, the only time they get involved is when you have hydrogen, because it only has the 1s orbital, so it's its valence, right? It's also helium's valence, but nobody cares about helium. It doesn't do anything. You can't, so in lecture notes it's written as 2px, 2py, 2pz. Do we need to draw that as well? No, just label them as p. I know that you know they're 2py. I'm going to assume you know that they're 2py, 2px, 2pz. We can't really differentiate them. It doesn't really matter which is which. And the problem is when you draw that and you draw one orbital, I'm going to get somebody thinking, well, does the one electron go into the 2pz or the 2py or the 2px? Is there a difference? There's no difference. They're all exactly the same. So let's just dispense with pretending that we know which axis what's attached to. Okay, so these are our 3 options. Oxygen can become sp3, sp2, or sp. These are the 3 settings on the blender, depending what you put into the blender. The analogy is falling apart. I'm going to give up on it now. Question. Which of these is lowest in energy, total energy, of all the electrons? No, you don't need to include the X or Y for the configuration. No. You got to guess for SP. These 3 electrons are definitely the lowest, but then we've got 4 at the, okay, good. No one's saying sp2. We're going for the extremes. Okay. The lowest total one is sp3. You can do the math if you really want to. But what really comes down to is in sp, you've got 4 electrons sitting at the p level. They are high energy electrons. And that more, and if you do all the fractions and stuff, or you can just believe me, it's up to you. You can do the fractions and stuff. The more electrons you have sitting up here, it overcompensates for any increase you get in dropping it through the hybridization. sp3 is always lowest E of electrons. Atoms will always go sp3 unless they have a reason not to. And there are 2 reasons not to go sp3. So, sp3. And sp3 is tetrahedral. Trigonal, linear. Trigonal planar if you want to be technical, which we probably do. So sp3 is the lowest energy configuration possible for any hybridized atom. So when do you use the sp and sp2? Why do those exist if sp3 is lowest? There are 0 lone pairs on the carbon. On this carbon over here, right? That's what we're talking about. All of its electrons are involved in bonds. Yeah. All second row elements. Well, okay, I shouldn't say all second row elements. Carbon onwards for the second row elements. So carbon, oxygen, nitrogen, fluorine. What I'm going to say are the real elements. All the other elements are posers, but like the real second row elements are like the organic elements. They have 4 orbitals, 4 valence orbitals. those 4 valence orbitals are either occupied by a lone pair or they're occupied by a bond. Carbon's making 4 bonds. It's got no rooms for anything else. It says linear under the SP. Linear. I'm not sure if that's any better. I'm a doctor. I chicken scratch. Goes with the territory. I do my best. I also don't know how to use a tablet. Next slide, please. There we go. I probably skipped like 7 slides. Okay. So SP3 is almost exactly. Why would? Man, you're like a plant. Noor is not a plant, but like not a plant like a growing plant like a tree, but you know I plant certain lecture thing. Why wouldn't SP3 be good? Let's talk about that. Okay. I'm going to give us an example which leads directly into today's lecture. So we're going to do this as a 2-parter or a 3-parter or maybe a 5-parter. I don't know how many parts there are, but there's lots of things we can do to talk about this molecule. Okay, I've drawn a condensed structural formula for a molecule. Can you please draw the Lewis structure? You can draw a Lewis dot structure if you like, but just draw a Lewis structure of that. So there's a bracket around the oxygen. And what that means is it's attached to the previous atom, but so is the thing after the bracket. So that tells me that the oxygen is attached to the carbon and the fluorine is also attached to the carbon. If I didn't have the bracket there, it would mean the carbon was attached to the oxygen was attached to the fluorine. But with the bracket there, I mean the oxygen is attached to the carbon, the fluorine is attached to the carbon. So give it a second for you to draw the Lewis structure. I really hope that you drew this. The nitrogen is attached to 2 hydrogens, which is attached to the carbon. The carbon is attached to the oxygen in brackets, and the carbon is attached to the fluorine. The fluorine already has 7 electrons. Fluorine can only make the 1 bond. That means the carbon must be making a double bond to oxygen, because carbon must be making 4 bonds, oxygen should be making 2. Does anyone not follow that? Okay. Let's talk about what the hybridization of these atoms is. And this is a trick question. And so we're going to pretend it's not a trick question. So I'm going to say, assuming that resonance does not exist, what is the hybridization of these atoms? And then we're going to talk about resonance, and then we're going to talk about orbitals, and we're going to talk about why things might not want to be sp3. So, assuming resonance does not exist, what is the hybridization of the hydrogen? Nope. Hydrogen only has 1 electron. Right. Thank you, Isaac. Hydrogen is always 1s. Always 1s. There is no example of hydrogen being anything else other than 1s. Okay, nitrogen, or S, you can call it S, that's fine. You don't need to write the 1. S is fine. 1s is fine. 1 doesn't mean anything. Okay, nitrogen. What is the nitrogen? Again, assuming that resonance is not a thing. Fatima says sp3. Dondra is in with sp3. sp3. sp3 is nitrogen. We're getting the sp3 crowd coming in. They are numerous. Noor has an sp2. How many things are attached to nitrogen there? There's 4 things attached to the nitrogen. You need 4 orbitals. Let's put the lone pair as a thing. I define lone pairs as things. There's 3 atoms but 4 things. I'll talk about why the thing matters. There's probably a much more technical term for it, but it's a stupid term, so I'm sticking with thing. There's 2 hydrogens, a carbon, and a lone pair. We need 4 orbitals. They all need to be occupied. We want to minimize energy. Unless there's a good reason not to minimize energy, we do sp3. So I am going to pencil in. I don't actually have a pencil. All I have is pens. I'm going to pencil in as sp3. This is not actually right. But we're assuming that resonance does not exist, and right now it is right because resonance does not exist. Okay, carbon. What is the hybridization of the carbon? sp2s. Sweet. And I saw the answer in there, which is because double bonds need a p orbital. So you need to have a p orbital left. So although it would love to be sp3, because that's better, it needs to have a p orbital to do a double bond. And if you have sp3, you have no p orbitals. So you can't make double bonds if you're sp3. So I want to just reiterate that point. Can't make double bonds if sp3 need a p. Okay, how about oxygen? I see SO2, that's probably a typo. It's sp2. Saw sp as well. Again, unless you have a good reason, sp3 is best, sp2 is second best, sp is worst. Nothing wants to be sp if it has a possible choice to be anything else. Oxygen needs a p orbital because it's making a double bond, so it must have a p orbital. Great, we got a p orbital. Everything else, we're sticking to an sp orbital. And since there's 1 p orbital, that leaves us 2 p's and an s. Mix them together, sp2. Okay, again, assuming resonance does not exist. Well, the double bond, yeah, the oxygen counts as one thing. The double bond is, they're going the same direction. So the oxygen is a thing, a lone pair is an atom, or a lone pair is a thing. The carbon's got no lone pairs. It's got 3 atoms attached to it, so it's attached to 3 things. The 3 things it's attached to is nitrogen, oxygen, and fluorine. And so it's going to be trigonoplanar. There's no lone pair. The oxygen is attached to 3 things. It has 2 lone pairs and a carbon. So it's trigonoplanar because there's 3 things attached to it. Yeah, so a double bond doesn't really come into it. It's like how many atoms and lone pairs are attached if you're counting things. There are other ways to think about this, but this is the way I'm going to be talking about it. If you learned it a different way, that's cool. Somebody said I learned about things as electron clouds. I'm going to be nervous about that because it's not actually right. The electron clouds are everywhere, and it's very confusing. And so that is actually a false statement. But for me to say it's attached to 3 things is a true statement, and it will remain true even if it's a massive oversimplification. Sounds kind of stupid. They're fixing my roof, and by my roof I mean Essex Hall's roof. And so that sounds like thunder out there. So I hope that's not interfering with things too much. Okay, fluorine. Assuming resonance doesn't exist, what is the hybridization of the fluorine? So I guess the question is, how many things is it attached to? Perfect. There are 4 things. There are 3 lone pairs and a single bond to a carbon. So there's a carbon and there are 3 lone pairs. That is 4. We are the counts, and we like to count. Like we only need to count to 8. Not like those fancy inorganic chemists who need to count to 12. I only have 10 fingers, and I'm wearing shoes. And otherwise, I could probably get to 11, but I am not physiologically gifted. So we have the fluorine as sp3. I'm going to draw that in blue as well, because that is also wrong. Okay. I just said that 2 of the things were wrong. So Alan said 4 things that the same as 4 sigma bonds, or in this case, there's only 1. It's sigma bond, it's atoms attached plus lone pairs. So fluorine has 3 lone pairs and 1 atom attached. That's 4 things. I guess you could say it would be equally correct to say count sigma bonds and lone pairs. But then just make sure you know what a sigma bond is. This is just like that, yeah. Okay, so let's take a look. What we're going to do now is we're going to draw something called linear. It's actually not. I got corrected. It is not a linear combination of atomic orbitals because that's actually an orbital diagram. And somebody told me I've been calling it the wrong thing my entire career, which is really embarrassing. So we're drawing a molecular orbital diagram using hybridized orbitals, or a VSPER diagram. I am probably still going to call it a linear combination of atomic orbitals because I was taught that, and damn it, I don't really care if it's wrong. It sounds about right. So I call this an LCAO model. John is wrong. But calling it a VSPER diagram just doesn't make as much sense. So what we're drawing is the atomic orbitals attached together. Yes, N and F are heteroatoms. So is O. Everything that isn't carbon and hydrogen is a heteroatom. As organic chemists, we believe in the purity of carbon and hydrogen bonds. You know, a not complete but not bad definition of organic chemistry is the chemistry of things that have carbon-hydrogen bonds. So anything that isn't carbon or hydrogen is a heteroatom. Stability trumps. Julia said stability trumps dropping energy levels. That is true. Heteroatoms are anything that's not carbon or hydrogen. Yeah. We're really exclusionary. Like the whole rest of the periodic table is not proper. Like the only proper atoms are carbon and hydrogen. Okay. Everything else is other. So what I'm going to do is we're going to draw the orbitals in 3D. So nitrogen. You're going to have to forgive me. I suck at 3-dimensional drawing. They no longer do this in Ontario high schools, but when I was going through high school, we used to have E grades. So you could have A, B, C, D, E, or F. And E was between 45 and 50, and it was considered a redeemable failure. You didn't have to retake the course, but it got put onto your notes, and you had to take the next course in the sequence and do better. I got an E in art. My report card in grade 7 art. My report card said John tries very hard, but he has absolutely 0 talent. And that's completely true. And it hasn't changed. So I'm very sorry. What I'm drawing here are 3 sp2 orbitals on nitrogen. We will understand in a second why I'm drawing sp2 orbitals. I'm drawing one coming out of the plane towards me, one going back into the plane away from me, and I'm going to draw circles for the hydrogens. Yes, this is going to explain why the nitrogen and fluorine hybridizations are wrong. Okay. Now I'm going to draw carbon. And I'm going to cheat a little bit. No, I'm not. I'm going to be a good boy. So and I've drawn oxygen. So one of carbon's sp2 orbitals is going back into the page away from me, and it's joining oxygen's is coming out of the page because oxygen's way back in the page, and so it's reaching forward towards the carbon, and oxygen has lone pairs in its 2 other sp2 orbitals. I'm going to highlight my p orbitals in green because, I don't know. Okay. Now fluorine, I'm actually going to do the same thing. It's going to look identical to oxygen. I am also going to draw a P, I'm going to draw an sp2. And I changed color and I didn't need to. And it's got 2 lone pairs. And so fluorine has 2 electrons that are somewhere. Nitrogen has 2 electrons that are somewhere. This guy's lone pair. Okay. we're gonna put 1 electron in each of these, and I need to make shade one of my p orbitals. Okay. So a pi bond is formed because you have 2 p orbitals next to each other. That's what a pi bond is. 2 p orbitals next to each other. That's it. So I've got a simple question for you. Is having a bond more stable than not having a bond? Yeah, having a bond is more stable than not having a bond. Always. It is always better to make a bond. Bonds are always lower energy than not having a bond. Okay. So just drawn p orbitals on nitrogen and fluorine. But John, you say, I don't know, maybe you don't say it that way. It's very dramatic. That can't do shit because carbon's got an electron in its p orbital. I can't add more electrons to a carbon orbital that has an electron in it. Well, who says carbon has an electron in its p orbital? Why can't that carbon electron be over in that oxygen orbital? And suddenly it's an empty p orbital. And it's an empty p orbital, and it's right next to another p orbital. And what is a p orbital next to a p orbital? It's a question. What is a p orbital next to a p orbital? Pi bond, exactly. So what this is resonance, what we are drawing here. We are drawing the resonance is trying to stabilize molecules. Bonds are more stable than not having bonds. If you can have a bond, you will make a freaking bond. So if nitrogen has a p orbital, it can interact with carbon's p orbital. If fluorine has a p orbital, it can interact with carbon's p orbital and make a partial pi bond. Why partial? Well, because oxygen's also making a pi bond with carbon. So what the hell is going on here and how do we think about this? This is what resonance is. It is allowing us to move the electrons around. Electrons are like us during COVID. I really don't want to be in my house anymore. I really want to be almost anywhere else. Like I'd even travel to the UK, and I don't like the UK because I just want to be delocalized. I'm stuck in one place. I am unhappy. I am full of cabin fever energy. I do not want to be in one place. I want to be relaxed on a beach in Mexico. I want to be everywhere. And electrons want to always be everywhere. And so electrons will try as hard as possible to create networks of things so they can go everywhere. That is what resonance is. So resonance is setting up p orbitals next to each other so that electrons can delocalize. This is the proper drawing of this thing. This is only possible to happen if the nitrogen and fluorine are sp2. If the nitrogen and fluorine were sp3, there would be no p orbital, there would be no possibility of a bond. You cannot make a pi bond with an sp3 orbital. And so when I went back and I said everything becomes sp3 because shit's lazy, unless there is a reason for it not to be, this is the reason for it not to be, because it can make a bond with a pi orbital. Yeah, sp3 has no p orbitals left, which is why the fluorine and nitrogen are not sp3. Because if they were sp3, they would not be able to make a p bond. That's why I said those were wrong. They are sp2. So everything, except for the hydrogens, and who cares about hydrogens, is sp2 in this molecule. So how do we, like, if you have to do this every time, you're going to go crazy, because we just spent like 20 minutes drawing this thing and it's only got 4 atoms in it. So that's not very effective. So let's think about a way to think about this. Blah, 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 sketch it out real fast. There, what was that, like 5 seconds? A little bit more than 5 seconds. I've drawn it in lone pairs. So with resonance, the way we can think about how to draw resonance is you're pivoting electrons. You can keep in mind, if you like, that you have those p orbitals that can interact with one another. But for a p orbital, for a lone pair to interact with an adjacent p orbital, that adjacent p orbital needs to be empty. And right now, that p orbital on that carbon is not empty. It's got an electron in it because it's making a double bond. So let's take care of that. So we are drawing an arrow. I know Dr. Hayward drew some arrows with you last class. I wanted to, it's an arrow, how complicated it can be. Apparently very complicated. So what I want to do is I want to highlight what I am doing here. First of all, negative charges on any atom are a result of having excess electrons. Positive charges are not a result of having excess protons. They're a result of having a deficiency of electrons. It's all about the electrons. So, like a positive balance in your bank account is because you have money. A negative balance in the bank account is not because there's something there, it's because you don't have money and you're overdrawn and you're about to be dinged with a really big fee that's going to make your balance even more negative. So we are moving electrons. Electrons move. Charges don't move. Negative charges don't move. Electrons move. And negative charges follow where electrons are. So what I'm doing with this arrow is I am saying that 2 electrons, why 2? Notice that my arrow is double-headed. There's like 2, it's an arrow. Arrows are normally double-headed, though we are going to see single-headed arrows later. It's double-headed, that means 2 electrons. They are moving from the bond onto the oxygen. Nope. Everything is staying sp2. Everything is always staying sp2. Once you have a molecule, molecules do not rehybridize unless they're doing reactions. These are not reactions. This is just a description of what the molecule looks like. It's all the same molecule. This is a resonance arrow. And I am indicating it with an arrow, which isn't any kind of arrow. It's just I am drawing things arrow. But a resonance arrow is double-headed. So back and forwards. So I'm using an electron flow arrow saying electrons are going from the bond between carbon and oxygen onto oxygen. And I'm using a resonance arrow to say the relationship between this molecule I've drawn on the left and the molecule I'm drawing on the right is that they are resonance structures of each other. Why is it negative? Because if I draw the formal charges on that, I would find it as +1. Now that carbon is positive. I'm not missing a lone pair on that carbon. There is no lone pair on that carbon. That carbon has an empty p orbital. If we want to go back to our drawing we just had here, what we essentially just did is I indicated that this electron moved over here. So they're both on oxygen. The oxygen is now negative. The carbon is now positive. Notice I haven't changed any of the orbitals. I haven't moved any of the atoms. I haven't broken any of the bonds, really. Or changed any of the hybridization. I guess I've broken it all bond here. But all I'm doing is I'm shutting the electrons in through p orbitals. Now this is positive. So now it can accept a pi bond with either the nitrogen or the fluorine, because they have 2 electrons in a p orbital. They don't want that, right? Because that's 2 electrons in a p orbital is bad. If you want to have 2 electrons in an orbital, make it sp3 because then you have lower energy and all that. We just talked about that. But it's got 2 electrons in a p orbital. It's got an empty carbon p orbital. We can make a bond because 2 electrons, 2 p orbitals, that's a bond. And we can do it with either nitrogen or fluorine. So how we indicate that here is I draw an arrow from the lone pair on nitrogen to the space between the nitrogen and the carbon. Not to the carbon, but to the space between. And that's indicating I am making a new bond. We're going to go a little bit over time here today. I promise once the labs start, we're not. If you need to run for something, you can run for something. Otherwise, the damn thing's recorded. It's nice about these whole remote things is that when I'm in the middle of a spiel, I don't need to cut off immediately. And now the nitrogen's positively charged because we do a formal charge count on a nitrogen. We've taken 2 electrons that were in a lone pair where they actually count for 2. We've stuck them into a bond. And you take only half of that, so they only count for 1, so we're kind of short an electron. Note too, the other way to know that you've done this right is the total charge in all these resonance structures need to be identical. 0, 0, 0, right? Because +1 - 1 is 0. So Jolene asked a really, I'm going to come back to your question, Jolene, because it's absolutely essential. Alea, you asked a really good question. It's basically the same question as Jolene. Julia is getting ahead of everybody. So Julia, I'm going to come to your thing in a moment, but the other two deserve their answers as well because they had really cool questions. Okay, so I'm just not going to have to draw a new structure, so I'm going to use a different color because the magic of electronics. So I could have equally have used 2 electrons from fluorine. Again, same situation if you go back to that previous slide. 2 electrons in a p orbital on fluorine, 0 electrons in a p orbital on carbon. You got 2 p orbitals next to each other. There's 2 electrons. You can make a bond. There is no no, that's not a free radical. That's me putting a little dot there because I don't know what I'm doing and my pen touched accidentally. But thank you, Amanda. That's a really good point. Is the middle structure like an intermediate? That's a really good question. Okay, so this is the first thing I want to talk about with this. Is chemistry happening here? Great. No, chemistry is not happening here. Are these different molecules? Right, there's no chemistry happening. They are not different molecules. They are the same molecule. These are all absolutely the same molecule. These are not flipping back and forwards. So this is where some people get confused. They see these and they go, okay, I kind of get it. Sometimes the negative charge is on oxygen, sometimes there's double bonds, sometimes the positive charge is on fluorine, sometimes it's on carbon, sometimes it's on nitrogen. That's incorrect. It is not sometimes on any of those. We are drawing it this way because we are stupid. We're humans. Our brains are not designed to do this. Our brains are designed to chase things on the savannah, right? We're trying to delve into the innermost nature of the atom. We are not designed to do this. What I'm drawing here is a model of reality because I am pretending that electrons are point charges that are in one place at once. And they're not. Electrons are not in one place at once. Electrons are waves, right? So the electron is just, the electrons in this molecule are distributed over the entire molecule. They're smeared over the entire thing. And we can plot densities of the electrons present. These four structures I've drawn here are four ways to describe the electron density in this molecule. They are not switching back and forth between these things, but together we can get an idea of where the electron density is. So somebody asked about the resonance hybrid. The resonance hybrid, I'm going to draw it in brackets here, is the weighted average of these structures. It's where the charges mostly are on this thing and where the bonds mostly are. So the way we draw that is we draw in all the sigma bonds. Everything that never changes is drawn as a solid line. You know, good, strong sigma bonds, those things are never going anywhere. They are good, strong sigma bonds in every single resonance structure I've drawn there. Everything else is dotted. No, I don't need two of them there, only one. Damn it, didn't mean to delete oxygen. The overall charge on this molecule is 0, so I'm not putting, if there was an overall charge, I would put something up here, but there's not, so I don't. And then I draw where the charges mostly are. Well, and I use a delta sign. So there's a big delta minus on oxygen. The oxygen is negative in 3 of the 4 resonance structures. I'm going to put a big delta plus on nitrogen, a smaller delta plus on carbon, and a smaller delta plus on fluorine, but maybe a little bit bigger than the one on carbon. That's the resonance hybrid. That positive charge, there's electron deficiency on nitrogen, carbon, and fluorine. And we're going to discuss why those sizes are different later. And there's an electron richness on oxygen. And there's a partial double bond between nitrogen and carbon, between carbon and oxygen, between carbon and fluorine. So this molecule is going to react as though the oxygen is slightly negative and the nitrogen and fluorine are slightly positive compared to what they should be. Yes, and as somebody pointed out, we can draw in the lone pairs. Two lone pairs on oxygen and fluorine, because those are always there. I get a little iffy about drawing the lone pairs on resonance hybrids because it's not clear the nitrogen lone pair and a fluorine lone pair, so it's perfectly fine to do this. I'd accept almost anything in terms of the lone pairs, unless you draw like 5 lone pairs on fluorine. That's obviously wrong, but I would accept you drawing 2 or 3 with the resonance hybrid. I'd accept either of those, and I'd accept a lone pair on nitrogen or not. All those would all be correct. So you can draw them or not. Just don't draw more than there could be possible in the absolute highest level of it. So yeah, 5 lone pairs on fluorine would be wrong, but 3 is fine, 2 is fine. Yes, what you'll be asked, if you're asked to draw the resonance structure, you would do all of this because you can't draw that without drawing that. Okay, let me rephrase that. It's possible to do. I can do this because I can do this in my head. I've been doing this for 20 fucking years. So you guys haven't. So there are some of you who might be able to do this by inspection. I wouldn't expect it. I'm not going to give you that credit. I need to see your work. It's also, if you screw up, then I can give you marks for your work. So I want to come back to Jolene's question. So if we use the amount of things to decide that N and F were sp3, did they just become sp2 so they can make a pi bond with the extra p? I think I missed the step when they switched. How do we know when they will go sp2? So here's the trick. They were never sp3. The fact that we assign them as sp3 based on 4 things is because we went with the rule, things are going to try and make everything sp3 because they're lazy. But then we forgot the thing, unless there's a reason that they shouldn't be sp3 because they can make a bond. So what you needed to realize is that they were adjacent to a p orbital and it can make a bond. So here's that. This isn't a rule, but it's a rule because it's always true. So my rule about hybridization. If a heteroatom, here we go with heteroatoms. But I'm going to change it. If an atom, because carbon can have lone pairs too in weird cases, is next to an atom with a p orbital, it will have a p orbital. Because if you have an atom next to an atom with a p orbital, and you have a lone pair, or you have an empty orbital, because instead of a lone pair, you have an empty, you just have your missing electrons in that orbital, and you're next to an atom with a p orbital, you will have a p orbital, and this can chain together. So you can have one where it's not clear, like we can see an example like, let's say we had this molecule. This guy obviously has a p orbital because it's part of a double bond, which means this guy's going to have a p orbital. And since this guy has a p orbital, this guy's going to have a p orbital. But it is not clear if I look at the oxygen first that if I look at the oxygen first, it's not clear that this has a p orbital. It's only clear that this has a p orbital because it's next to an atom with a p orbital and has a lone pair. Less than or equal to. Because you could have 2 p orbitals, because you could be sp. You can't have 3 p orbitals to make a bond. Partial promotion, Alia, do you mean electron radicals? So adding an energy to bump an electron up an energy level by partial promotion? If so, we will talk about that later. Yeah, we're going to talk about radicals near the end of the course because radicals are complicated. For the most part, we're not going to worry too much about them. Yes, that rule can carry through a whole molecule. Yes. Yeah, you can actually chain an entire huge freaking molecule together. Now, you break that chain, clearly, whenever you run into an atom attached to 4 different things. Like a carbon with 4 bonds, it can't have a p orbital because it needs all 4 sp3. So do we move the double bond to the other side of carbon since it's not sp3 and make a pi with n? Well, I would still draw it this way because the resonance structure with the pi with n would be this. And we're going to talk about this starting next class. We're going to talk about why some of these resonance structures are preferred over others. So I've drawn 2 arrows there, one after the other. I think this is where you're going with this, Jordan. So what we did was we used the lone pair on nitrogen to make a new double bond with carbon. And we broke the carbon-carbon bond because we needed an empty p orbital to interact. The other reason we broke it is because if we had left it intact, that poor carbon would try to make 5 bonds, but it's only got 4 orbitals, and you can't make 5 bonds with 4 orbitals. That's not possible. It's called a Texas carbon because things are bigger in Texas, and they're also wrong in Texas for so many reasons. So the electrons got pushed onto the other carbon. So you can draw this. These are resonance structures of each other. And I think that's where you're going, but everything here hasn't changed hybridization. The hybridization of any atom in any resonance structure is the same as its hybridization in every other resonance structure, because you're not allowed rehybridizing between resonance structures. The only thing we're doing is we're moving electrons around in p orbitals and just like, I want some over here, I want some over there, whatever, move them around in p orbitals. But I'm not allowed changing the hybridization in resonance structures, because if I change hybridization, I change geometry, right? Because if I go sp3, suddenly things aren't flat, they're now tetrahedral, so bonds moved. But I just said that these are not interchanging. These are all the same thing. This is our minuscule little simian brain trying to make sense of electron clouds. And we're stupid. So I'm drawing arrows and dots and electrons and bonds, but nature doesn't see that, right? Nature has, here's a molecule, here's how the electrons are distributed over that molecule. That's it, right? Molecules are like clouds of electrons around atoms. That's not very helpful. So bonds are helpful to think of things as bonds. If we really want to confuse you, there's no such thing like this covalent bond cannot be thought of independently of this covalent bond, because the electrons there are interacting all the time and are not separate. But if I try and think about that, my brain will explode. So I am not thinking about that. I am treating this model as a model, and I like my model because I can understand it. Is the number of available p orbitals related to the number of resonance structures we can have? Like total p orbitals related to the number of resonance structures? Yes, but I don't believe there is a precise equation. Yes. So one hybrid screen must cover them all, right? This drawing I have here, this drawing of where those orbitals are, not where the electrons are in the orbitals, but where the orbitals are, covers all the resonance structures. Because I'm not allowed moving anything there. I'm not allowed rehybridizing it. I'm not allowed switching the position of any of the atoms. I'm not allowed rotating bonds. Everything is frozen. And I need to be able to draw all the resonance structures with that. Okay. I am officially done this lecture. So if there's any follow-up questions, I can answer those now. Besides, what the hell just happened to me? That's a good question. And what I'd recommend, if that is your response, is what the hell just happened to me, please relook at the resonance lecture that I posted. If that doesn't help, because it probably won't, because if I didn't help you here, I probably won't help you there. Take a look on Wikipedia, read your textbook. I'm going to say this is probably the most important concept in the course. Yeah, I think I'm happy saying that. This course could be titled Organic Chemistry, How to Stabilize Your Charges. Resonance is a really important way to stabilize your charges. Ali, yes, sir, my Wi-Fi cut out, so essentially sp2 is just two p orbitals bonding when atoms are next to each other. Yepers. So you're going to maybe want to rewatch this because I think I covered that. But when you have two atoms that can make a pi bond next to each other, if they can hybridize to make the pi bond, they will hybridize to make the pi bond, which will force somebody who would have otherwise been sp3 if he was out on his own to become sp2, because he needs to hybridize to make the pi bond, because he needs a p orbital to make the pi bond. Yeah. What are the other resonance structures of the molecule? This one here. Deepashika, is that what you're talking about? This molecule? So we're in textbook. Can we practice this? I think it's under the resonance section. I think that's chapter 2. Maybe it's chapter 3. It's one of those chapters. I think I also have some of those in my first assignment. I think I called it assignment 0 or assignment X or assignment -1, because I didn't go back and renumber the assignments when I added more. So I added earlier assignments, and they were earlier than 1. So the other resonance structure I can draw for this is, this is a really stupid resonance structure. This molecule is stupid. This molecule doesn't exist, I think. I have a feeling it would detonate. But this is a perfectly valid resonance structure. It's a stupid ass resonance structure. But it is a valid resonance structure. You've got that. I could also draw each of those two arrows I drew them in pairs of arrows. I could have drawn them one at a time as well. So it would give me 2 more resonance structures. And I will leave that as an exercise for the viewer. So basically sp3 is not good because it limits the ability to have pi bonds. Exactly, Nor. So sp3 is good when you can't make pi bonds because it's the most stable way to keep your electrons. But if you can make a pi bond, you make a pi bond. And if you're sp3, you can't make a pi bond. Right, so Jolene, so in conclusion, F looks sp3. I'm going to change it. You said is. I'm going to say F looks sp3 because 3 sets of lone pairs in 1 bond. But because it can make a pi bond, it will be sp2 because it wants to make a pi bond. And making that pi bond, making a bond is more stable than not making a bond. So yes, sp3 is more stable than sp2 in isolation, not thinking about bonds or anything, just where the electrons are. But, you know, it's the difference between strawberry jam and raspberry jam on my toast. I like both. You know, I think I like raspberry jam a little bit more than strawberry jam. I had to think about that, but they're pretty close. But making a bond is like putting like chocolate ice cream on my toast, which I probably would really love. I don't think I've ever done it before, but that sounds amazing. And that's just so much better than jam. So I'm like distinguishing 2 little different types of jam, whatever. Chocolate fucking ice cream I'm putting on my toast. So I'm making a bond and screw the jams. So the jam difference doesn't matter. I don't think that was a helpful analogy because you might not think that chocolate ice cream on toast is a good thing. Maybe Nutella. I think we can all agree Nutella is a really good toast topping. Okay. So Madison, for the methane example you gave earlier in class, why did we move 1 electron from 2s to the 2p? I didn't actually. What I did was I was sort of examining the fact that you could consider that fact. You could consider. Man, the problem with doing all this and erasing things and putting them back in is when I post these notes afterwards, they only really go with the video. So, oh well, that's what this is about. If you want a video and with proper all written up notes and stuff, that's what the other ones are for. This is for, you know, doing this. If you're trying to think how can I make 4 bonds with this carbon, you'd have to do that if you didn't hybridize. You would have to move the electron up, so you'd have 4 half-filled orbitals so they can make a bond. Because if it's full, it can't make a bond with an H with a single electron, because the H needs to put that electron somewhere, so you need a half-filled orbital. So I was demonstrating theoretically you could move it in there, which would again give you 4 half-filled orbitals, which can make 4 bonds. But that's not what happens. What actually happens is molecular blender for degenerate orbitals. And that makes sense of why we have 4 bonds. Oh, good. I'm glad you said, oh, okay. WTF is a fully appropriate response to any of my explanations because that means I did it wrong. So just to clarify, when we ask for shapes, we're going with basic shapes, ignoring the effective lone pair. I'm not going to ask you for the shape of an atom because I'm always going to be thinking about shapes in terms of the lone pairs. So I'm always going to think about oxygen being tetrahedral. I'm thinking about where the orbitals are. So it's not like I know in high school organic chemistry, if you had said that the nitrogen, if you had said that this nitrogen was tetrahedral, they would yell at you and say it's not tetrahedral, it's trigonal pyramidal. But yeah, that's true, I guess, but I really care about this as being sp3. And this nitrogen is sp3 because that lone pair is not adjacent to any heteroatom with a p orbital. There's nowhere for those electrons to go, so they're stuck in an sp3 orbital. So if I asked you for the shape of that molecule, you said tetrahedral, I'd give you the mark. If you said trigonal pyramidal, I'd give you the mark. I'm not going to ask you for the shape of the molecule. Like, you do you. we're going to apply that to things. I'm going to ask you about that. So before determining hybridization, should we just draw? Yes. So Melisha asked the absolute. I don't know if you pronounce your name Melisha or Malika or Malika. So before determining hybridization, should we first draw all resonances? Yes. You can do them in your head, or you can draw them on paper. Initially, start drawing them on paper. Once you see enough of them, you're going to start doing it automatically in your brain. Now, I do not care about hybridization of atoms for their own sake. This isn't like because I get high on whether an atom is sp2 or sp3. It doesn't matter, really, normally. But whether an atom is sp2 or sp3 affects how it reacts. And if you can't tell if an atom is sp2 or sp3, you're not going to get right how it reacts. And how it reacts is important. So, yes. I just want to give the rationale for why I'm doing this. It's not because I'm some sort of like geometry Nazi.
Okay, thank you. It's Milita, by the way, just because you asked.
Mili.
Milita. It rhymes with
Militsa.
pizza.
Okay.
That helps.
Militsa. Sure, there we go. I will pretend that I will remember that, but I won't. I will try because I've seen you actually answer other things in the chat here, so memory's a little bit better than that. Melissa, thank you. I'm seeing greats and have nice weekends, and so I think we're done.
Question.
Okay.
Yeah. I know I've had my hand up for like half the lecture.
Oh, I'm really sorry.
Yeah, no worries. So I wanted to ask you, did you post the game link for naming of molecules yet?
Yes, I believe it is under the resources tab on Blackboard. Let me just double check that. It also might be, maybe it's also linked in the syllabus. Let me just please do this right. No, it does not seem to be in that. Did I link it in the syllabus? I might have hyperlinked in the syllabus if I was smart. Yes, I hyperlinked in the syllabus.
What page is that?
Page 8. It's the Org Chem 101. Here, I'm gonna move my syllabus. Damn it, where's my syllabus? I just had it. Where'd I put it? Was it in? Oh, it was in my, okay, it's my Blackboard. I don't have any tests on here yet, so it's all good. So there's my syllabus. Yay, syllabus. Page 7, there's Zoe. Page 8. So click on that, organic nomenclature.
Okay, second question. You discussed 4 roles in your YouTube video there that were talking about charge stability. I just wanted you to maybe briefly go over that and explain
We'll cover that next class.
Oh, okay. So, oh shoot, I thought I was behind. I don't know.
You're ahead.
Okay. Moving on. Third question. Oh, yes, it's about the resonance structures that you drew. So you were talking about how you would put a negative sigma bond on the oxygen and positive sigma, I mean, the fluorine, nitrogen, and carbon in the middle were all positive.
Yeah.
And you based that off of the resonance structures that you drew here, but you also said you could have drawn in more resonance structures. How do you know what
for this one? This one I couldn't have. I said for this one I could draw some more resonance structures. This one I think we drew them all.
Okay, and you can tell you limited it out with resonance structures because.
So one thing is I drew one arrow at a time here. Over here I drew 2 arrows at a time, right? So whenever you draw 2 arrows at a time, there's always a structure in between where I can move one of those pairs of electrons and not the other one. So there's at least 2 more resonance structures. There are 2 more resonance structures for this one.
Okay.
They're not very important resonance structures. And we'll talk about that with charge stability later. Here, what I did was I moved one electron at a time. I basically ran out of chains of electrons, places to move them to. And so you have a good question there, and I'm trying to think how to best make sure that I am addressing it. I think that there is no way I can move a lone pair or a pi bond from any of these four structures and generate a structure that isn't previously generated.
Okay.
Yeah. And that's how I know. And so notice what I'm doing is in here, the rule is the electrons can move from a bond onto the adjacent atom, or they can move from an adjacent atom to the space between two atoms if the other one is positively charged. That's the rule for how if I'm drawing a single arrow, that's the rule for what I'm allowed doing.
Positive charged and also neutral in charge, right? Because then
well, it needs to be able to accept an electron.
Okay.
If it needs to have an empty orbital. If it can be neutral if it has an empty orbital to accept an electron. Now, not quite true. I think there's one more resonance structure. There's a few other resonance structures I could draw. There's stupid resonance structures, and they're the direct opposite of the resonance structures I've drawn here, so they don't count. But I could draw a resonance structure where I move the electrons from a double bond onto a carbon. That follows the rules. There's nothing wrong with that. Now, if I did that, I would have a nitrogen, and if I count the formal charge, it would be plus. It would be double plus nitrogen. It would be a negatively charged carbon. The fluorine would be fine, and the oxygen would be negative. That is a really stupid resonance structure because I've just put two positive charges on an atom, and I put two negative charges next to each other.
That's going to be very unstable. So.
And it's the exact opposite of this guy. Like any amount that this contributes is directly opposed by this guy in the middle. And this guy's far more stable than the guy on the left. So like any amount that this would contribute to the resonance hybrid kind of gets canceled out by a tiny fraction of this because this just doesn't really exist.
Okay. Yeah, sure. That works.
Like,
I guess
because like it's like this is like if you count numbers, this contributes like 100. This is the direct opposite, so it's like -2 or -1. So it's, instead of being 100, it's 99. Who gives a shit? But this is just here because it's kind of subtracted away. It's the exact, like they're just, one is positive, one is negative. They're exactly the opposite of each other.
That's kind of like the jam analogy. I don't really get it,
right.
But it's okay. It's okay.
Maybe it's like the jam analogy. I don't think so, but that's okay. If you see the analogy there, I don't give a shit. Whatever works for you is good.
Okay.
Yeah. So the rough outline confuses you. Here is the rough schedule outline. We are currently, this is Friday the 17th. We should be talking about atomic and molecular orbitals and VSPER theory. And oh look, we were talking about atomic and orbitals and VSPER theory. So you should be reading that part of the syllabus. The syllabus conveniently has sections. Oh, look, atomic, molecular orbitals, and VSPER theory, more 1, more 2. So you should probably be looking at these lectures, these videos, and clicking on those.
Mr. Trent.
Dr. Trent. You call me lots of things, but not Mr.
Oh, okay, Dr. Trent. I have one final question. So, yeah. Science caution card that we need, if our first lab, which is on Tuesday for me, I believe, is going to be online, do we need that card in by then or no?
I don't know if you need a science caution card if you're doing it online.
I'm doing it online like in person.
You're doing in person, but your first lab. Okay, you're doing in-person labs, but your first lab is online.
Yeah.
Yes. I don't know.
Okay.
Everything lab related is dealt with by my colleague, Dr. Eichhorn.
Yeah.
we talked about the labs. I said, sounds good, Holger. He said, what are you teaching the class? I said this. He says, sounds good, Trent. And we went our separate ways. We like each other, but we're really dividing up the work on this.
Yeah.
So I think you would need to address that question to him. I think it should be fine because I don't see how you could possibly break stuff if you're online. Though the ingenuity of our students never ceases to amaze me. So.
Shit. Oh.
Okay. Good. Everyone's leaving. There's nobody here left. I think we're done. Take care, everybody. How do I stop recording?